Good morning. I thought it would be helpful to continue on our discussion of constructing the unit circle in trigonometry by showing how all of the ancillary trigonometric functions can be read directly off the unit circle merely by extending it beyond the points we normally view. So beyond the boundaries of the circle lie other functions, and it's fairly easy to draw them. Let me show you first what it is we're going to accomplish here. This image shows all of the trigonometric functions plotted, and you see the sine and the cosine. Here we're looking at an angle of 45 degrees, but you also see the tangent, the cotangent, the coversine, the versine, x secant, x cosecant, or rather the x secant, the cosecant, the secant, and the cotangent and the tangent. So it would be helpful to understand what it is this image is showing and how we might go about calculating it. Let me transition back to my drawing surface. And we'll just use our compass to draw a quick construction line. All right. Let me center this relatively straight, and then we'll just start by drawing a circle. And then if we place our point at the edge of the circle where it crosses the construction line, we can draw a second circle of equal size that creates what's called a vesica Pisces. Looks like a Venn diagram. And from the vesica, we may draw a perfectly vertical line. Perfect in the sense that it's derived from the circles and not from our eyeballing it or something. And so now we have, the camera distorts this slightly because it's angled ever so slightly to the surface of the table. But what I'm looking at is a perfectly vertical line and horizontal line, with this being a perfect right angle right here. And so now we'll construct our seed of life and flower of life in order to get to where we may draw the 45-degree angle perfectly. We don't have to draw these other quadrants here. We can just draw on the top right side. But I will draw the seed of life just because it's interesting to draw, and it doesn't take very long. and I'll recenter our vertical line to pass through the center of the seed. Show something interesting. Okay, so now we have that familiar seed of life image right here. In the center will be our origin point right there. So I can draw another vertical line because I have two vesicas, one right here and one below it, that I can use as a guide for my ruler, and I'll erase the other one later. The important point is, even though I'm drawing these lines, they don't really exist. They're just guides. They're often inexact when you start drawing it with relation to the circle. Even you can see there's a slight divergence in the parallel nature of the lines. I mean, they should be perfectly parallel, but the human hand and the vagaries of using a metal ruler will create these distortions. So it's really important to rely more heavily on the circles themselves to create the verticality. I'm just gathering a few materials that I might need. Okay, I'll do that later. Okay. I'll just make these lines a little bit more prominent and erase the one I don't need anymore. And there's no reason not to take your time with this. I'm trying to make it bold. And then the horizontal line. Similarly, there are these two petals of the flower now, which create a better guide for the horizontal nature of the line, and you might see it change slightly. Maybe not. We're going to focus just on this side, this quadrant here. And there we have our x and y axis, or our cosine and sine axes. Make that a little bit more bold. Okay. Now what we want to do is we want to find a point at which we can create a right angle, a 45-degree angle. This is a crude way to do it by locating what appears to be 45 degrees somewhere between 40 and 50 right there. But let's see if the circle provides a more exact way. Let's just see. Does the circle provide a way forward? The way to discover this 45-degree line in the circles is to just keep drawing circles. As I draw these wider and wider array of circles, you'll see other flowers emerge, or seeds, seed pods, however you want to refer to them. They look like little flowers to me. Okay. So let's see if our 45-degree line is more apparent now. We can use this protractor with the angle arm, or we can use a watch. If we think of time and the unit circle in trigonometry, the similarities are quite staggering. 45 degrees represents the time of 1:30 on a clock face. So if I take my watch and wind it back to exactly 1:30 and place that clock face as best I can right over the origin, I'll see if there isn't any point yet emerging that will allow me to draw a perfectly 45-degree line right through the origin from the hour hand of the watch. It didn't seem immediately clear to me that there was. Maybe there was, but it doesn't matter. There's no harm in drawing a few more circles to make this more clear visually. I should add that I don't know where the 45-degree line is in advance of making this video. That's the whole point, is that I'm assuming you don't know where it is. Maybe you do, but you may only know in a vague visual sense where 45 degrees is. We want to see it emerge from the circles themselves. So I'm just trying to be exact here. And what I mean by exact is that I want that 45-degree angle to emerge right out of the circles so that I'm not relying on the inaccurate straight lines that I've drawn. Since I know they are implicitly inaccurate, I want the implicit 45-degree angle to emerge from the geometry of the circles. So my whole process here is to just keep drawing circles until I see what appears to be correct. And then when we finally draw the 45-degree line, it will be, we can be sure that, if you down to the micrometer, it will be right, at least in the theoretical sense. So now I have a number of little petals or small seeds, if you wish. It's not important for this video, but if we take just one of these little petals and connect the dots, you can see geometric shapes emerge from that. This is a platonic solid that I'm drawing. It's a hexagon. It's just an interesting byproduct of what we're doing, that we're creating lots of geometry here. Lots of shapes can be found. But let's see if our 45-degree angle has emerged yet. Let's go back to the watch. 1:30. I'm seeing something here that looks right. Let's see if that doesn't give us what we want. Now here's a cheater trick. This is a square. The sides are of length 1, and the hypotenuse is of length square root of 2. Again, this is not an exact tool, but I know if I put it on the horizontal axis that my hypotenuse will create a 45-degree line. Let's just see if I've got anything to work with yet. Okay. Do you notice that right here in the center of the hexagon that I drew, there is a point that this and the origin seem to share on that line? So maybe that's a 45-degree angle. So I'll draw kind of a temporary line just to see if I'm getting at it. We go back to the watch to check. It looks like we have indeed found a, yeah, the camera's not doing that justice. It does indeed look like we found a 45-degree line. Even though the camera it's tilted slightly like this, so it's distorting what you're seeing slightly, but it's straight. If I put my protractor back on the origin and make sure that everything's nice and straight, then you'll see right inside this little opening that line, and that's on 45 degrees. So now we know we have a 45-degree angle, and let's see now where we want to go again. Let me show you that larger trig function graph. I'll just turn it off and turn it on so you can see that the line we drew is 45 degrees. If I center that graph right over our own graph, it makes it a little bit more clear that that's in fact what we did. So this is where we're headed. First, I just need to draw a circle to make a unit circle, and then we can find our sine and cosine for 45 degrees, and we can then derive all these other interesting functions from the graph visually. It doesn't matter where I choose to inscribe a full circle. It just matters that I'm consistent with it. So I'll open up the compass and find a point that I'm comfortable with. And why not choose the center of our hexagon as our point? It doesn't matter. In another video, I'll show how we can add phi and the golden rectangles to this image, but for now we'll just limit ourselves to the basic trig functions. We're not here to calculate them today, we're here to draw them. The more intuitive thing is to draw and not compute. I'm just going over this a few times so the camera picks it up better. Okay. All right. There were other ways, of course, to draw this. If I had centered, for example, if I'd centered my original construction over here, I might have found other places to draw my 45-degree line. There may have been other strange correspondences. Let's see, just for fun, if I'd put it originally there. It looks like that pedal there may have been 45 degrees, maybe not. So if I could have drawn through this point and that point there. Maybe. I don't know. It doesn't really matter. The point is this flower of life, the wonderful circles, you'll find many places where these perfect angles emerge. Okay. Now it's fairly simple to draw from just visually. Remember that in mathematics, this axis here is the y-axis, and this axis down here is the x-axis. But for the purposes of coordinates, this here, the y-axis is now going to be the sine, and the x-axis is going to be the cosine. So in a plot where we have coordinate points x, comma y, what we're drawing is, or what we're finding is the cosine and the sine. So when I find this vertical distance between this point on the unit circle and the horizontal axis, that perfect right angle there will be the sine of this angle right here, which is theta, and we know that theta is 45 degrees. So let's see, and I like, again, many people say, why do you need the circles? Well, look, if I try to put a straight edge on this and find a perfectly vertical line, if I was just eyeballing it, I would have no reference point. But look, the point of this little petal here, the center here, it's just remarkable that right below it, there's another point. And it's implicitly true that if I draw a line that merely connects these lines and I let it go down to the origin, that I've created a perfect right angle. I just find it remarkable. So now this is a perfect right angle of 90 degrees. Since this is 45 degrees and this is 90 degrees, and we know that all of the internal angles of a triangle add up to 180 degrees, I know that this angle here is also 45 degrees. And that's important because the 45, 45, 90 triangle has a special property. I'll just quickly draw one that isn't intended to be geometrically perfect, but it will show the proportions. if this is a 45, 45, 90 triangle, then this side length of 1, this side length of 1, this side length is the square root of 2. In trigonometry, we know that this distance is not 1. It's something less than 1 because this distance is 1. We know that the distance from the origin to the point at which the circle crosses the y-axis is 1. That would be the sine of 90 degrees is 1. So we know that that equals 1. Just as we know the distance here to here is 1. So the cosine of 0 degrees or 360 degrees, however you want to think about it, is 1. So this point, it doesn't go all the way up. So that's less than 1, and this is less than 1. The good news is that because it's a 45, 45, 90 triangle, this distance and this distance, these are equal distances because of this special relationship, 1, 1, square root of 2. Because it's a 1-1 relationship here, I can make this anything I want. And we'll go into more depth in another lesson, but this can be the square root of 2 over 2. And this can be the square root of 2 over 2. And I haven't violated any mathematical rules to make these two distances square root of 2 over 2. What I need to now recompute is the new hypotenuse if I want to know the distance here, the hypotenuse distance. And you can do that using the Pythagorean formula. But because we're not here to compute things, we're here to draw things, we'll just move on with just knowing that this is the distance on a unit circle. So if I'm going to label this vertical distance here is the square root of 2 over 2. And that would be the y-axis. So this is the sine. This is the sine at 45 degrees. And similarly, this horizontal distance down here is the square root of 2 over 2. If I can just extend my dots down a little bit. This distance is the square root of 2 over 2. And that's equal to the cosine at 45 degrees. We can already see many interesting relationships emerging, but first I need to plot this point. I need to plot a distance from here where the 45-degree ray hits the circle. I need to plot where that is on the y-axis. This looks a lot like a supply curve. in economics. And again, I don't need to think because my little flower petals give me a perfect guide from that point straight through to the y-axis. Interestingly, I now know that this is a perfect square because it's 90 degrees, 45 plus something equals 90 because this is also 90 degrees. And similarly, I know up here that this is 90 degrees. So this box that I just formed is a perfect square. And there are a lot of interesting things we can do here with we can derive the golden section, the golden rectangle from this, but we'll just continue. It's in the things we might be interested in is this distance here. The distance from this point to this point. See, this distance we've already seen is right there. It's the sine of 45 degrees. I've taken this vertical distance and it's over here now. Because it's a square, the sides are of equal length, so this distance is also square root of 2 over 2. So this is interesting. I don't know what that is. We'll go back to our table or our function graph and see what that is. But over here, similar, there's something going on here. This is interesting. Now, in order to plot other things that are interesting on this graph, we have to draw a tangent line to this point. This becomes difficult. It's one of the harder things to do when you're drawing trigonometry visually, because how do I know exactly where to put my straight edge to draw a tangent line? A tangent line would be a straight line that touches the circle at just that point. But it touches, it has to be very special. I have to be very careful about where I draw the line. Otherwise, I'll be off. You know, it's visually it's not clear to me where the appropriate place to draw the line is. I mean, I can use this square to see it visually, but I'm not actually. I see one point here that appears to be a tangent point, that intersection, but I'd like to see just one more point that might be relevant. So if I draw more circles, that might emerge. Let me reset my compass. Okay, so make sure I got it reset correctly. And big surprise, let's just draw some more circles. Oops, is that right? Gotta be careful. Yeah, I was just about to draw a circle that shouldn't be there. I need to be more careful. Let me start from a point I know here. It's easy to do, by the way, to draw circles incorrectly, especially when you've drawn in vertical lines and inscribed big circles. It's easy to get off track. Okay, so now I can draw this circle here. I like to think the circles are there, but that big circle, the unit circle, and those lines that I've drawn, those aren't really there in the sacred geometry aspect. Just the, now that's the point I was looking for. Oops, it's gonna walk away from me. Okay. Let's see now if we have, oh, I need to continue down here a little bit. Now let's see if our tangent line has more or less emerged. Oh, perfect. Yeah. You have to love geometry because the top of this vesica right here, that forms a tangent point. See? And then similarly down here, and we're showing, if I, this straight edge down here, this point here. So this vesica right here, the bottom crosses the x-axis. So that forms a point that is going to help me draw a perfect tangent line to my unit circle. So all I have to do is lay a straight edge on there and they should all connect. Perfect. So now we're going to draw our tangent line. Only part of this line is actually the tangent. The other part is the cotangent, as we'll see. I'm just going to make it a little more bold. Okay, great. So visually, you see more geometry emerging. It's like, if this is the sine, here's the top of the circle. So this distance is interesting. This distance might be interesting. The distance from here to here might be interesting. Here's another circle that just emerged out of nowhere. That distance is interesting. This whole distance might be interesting. Certainly the point here to here will be interesting. That's the tangent preview. And then this distance here. So we also have, this is the point where the unit circle is hitting the x-axis. But then this distance here might be interesting. No, I don't want to confuse anyone with that there. Let's superimpose our original, the graph on our image to see how close we're getting here. So we know that if I fade out on it real quick, just as I fade out on this, keep an eye on what's showing. Okay, let me fade it back in now. And fade back out. You see what we're going to draw now? I'll actually pull that image up and put it in our field of view here so we can refer to it without having to keep fading in and out. Let me do that. Yeah, so there's what we're getting at. If I use some colored pencils, might help. So this distance from here to here is the cosecant. That whole distance is the cosecant. This is the cosecant. It's abbreviated CSC in that diagram. Let me bring that up a little bit. Cosecant. So this distance here from the top of the unit circle to the point where the tangent hit the y-axis, that's the x secant. use purple to draw that. Let me pull this out a little bit so you can see what I'm doing. This distance is the x secant. We're not computing it. We're just highlighting that that's what we're doing. That's what it is, in fact. This is the x secant. Now, what about this little distance here? This is called the cosine. Cosine. These things, these different points that we're plotting have many uses. Some of them are navigational. Some of them relate to surveying. A quick Wikipedia search on each term. I meant to write that this was abbreviated as EXC. SC. Oh, I'm sorry, I made a mistake. So this is the x cosecant. Important difference. The x cosecant. Not the x secant, the x cosecant. XCSC. X EXCSC. X cosecant. The x secant is actually this distance here. That's the x secant. And this is the x cosecant, which if you look at the graph, they're the same distance, but one refers to the sine aspect because it's the vertical. The x cosecant is the vertical aspect of the distance, and the x secant is the corresponding horizontal aspect. But we'll label that in a moment. All right, this little point, this distance here that I was drawing in green, this is called the cosine. So I'll just make some dots. It's getting crowded. Okay, this is the cosine. CVS is how it's abbreviated, and it's the sine. And that is the vertical aspect of this. You see down on the, there's a, it's complement down here on the x-axis. That's just the versine. This distance right here, the versine. Because we're using a 45, 45, 90 triangle, these are equal. But if they wasn't a 45, 45, 90 triangle, these would take different values, depending if it was on the y-axis or the x. Okay. This distance here, let me shrink this a bit. The distance from here to the y-axis is the cotangent. So just go back to pencil for this one. That's the cotangent right there. COT for cotangent or cotangent. And if that's the cotangent, this distance here, which in a 45, 45, 90 triangle will be equal, you can see it visually. This is the tangent line right there. That's the tangent. Let me erase this. That's the tangent. Let's just finish labeling. The distance from the origin point, the origin point here to the point at which that tangent line hits the x-axis, that whole distance is the secant line. It's getting lost in the visual here, but this is our unit circle line. And we've actually extended, the tangent line has extended all the way out past the point at which the unit circle line has impacted the x-axis. We've gone out here now. Now this whole distance, so the cosine distance right there, plus the versine distance right here, plus the x secant distance here, all of those together add up to the secant. Let me erase a few things. We don't get lost. This whole distance is the secant. SEC for secant. That whole distance is the secant. So let's go back and just finish this off. If that whole distance is the secant, this distance here is the cosine. And this distance here, this distance here is the versine. And that corresponded to the coversine up here. Notice that the secant line down here with a 45, 45, 90 triangle has its cosecant equivalent on the vertical axis. So there's something maybe emerging in your mind that when it says cosecant, coversine, x cosecant, that those are referring to the vertical side of things, and the secant, the versine, and the x secant are referring to the horizontal aspects. I don't know. It seems to be so. Put it that way. So I'll label the versine with the brown pencil. That's this distance here from the end of the cosine to the point at which the unit circle crosses the x-axis. This distance here is the versine. This is the versine here. And then this distance right here is the x secant. And I haven't used orange yet, so we'll use orange here. This is the x secant. This is the x secant. X secant, and that's EX SEC. Right there. Now let's double check that we've labeled everything. And we have quite a number of things labeled. Something I don't know, but I'm interested in, is what the name would be. And if you know, or you can find out, please put it in the comments section. But I'm interested in knowing, and I in the limited research I did, I couldn't find it, but because I don't really know how to ask the question to Google. But what is this whole distance here called? This whole distance. In other words, the cotangent plus the tangent. What is that called? If you know, please inform all of us, and I can add it to the description of the video what that final piece is, or superimpose some text. So let me just finish off by overlaying these. Using sacred geometry, we have found all of the things that are plotted on this trig functions graph, and we did it using the circles. If we go back, we see that the key was to find the tangent line. Once we found that, everything fell into place. But we needed sacred geometry not only to create these perfect right angles and a 45-degree angle, but we needed sacred geometry to find that point there and that point there. Without those 2 points, I never would have known precisely where to put my straight edge to create a tangent to 45 degrees. The 45-degree angle. I needed that. I think this is a much clearer way of learning all of these trig functions than just memorizing the arithmetic relationships. For example, I don't need to be a genius to know that if I want to find the cosecant, I can add sine, which is here. This is sine. Sine plus coversine plus x cosecant equals the whole distance, which is the cosecant. And similarly, if I have the down here, this is cosine. Cosine plus versine plus x secant equals the secant. And if I was missing just one of those pieces, I could easily use the others to find the missing value. Another thing is, because it's a 45, 45, 90 triangle, and all of the x cosecant and the x secant are identical, and the coversine and the versine are equal as well, and in fact the sine and the cosine are equal. If I needed to find any of these points and I had their corresponding trig function values on the y or the x-axis, I could find them because they'd be the same. If I had everything down here and I needed the secant, but I was missing the versine value, but over here I had the coversine value, well, that's the same. So in this one special case, you can do that. Don't take that and think I can always, these are always equal, because it's only, literally only in the case of a 45-degree angle that this relationship is true. Similarly, I find the tangent to be one of the more difficult things to visualize. You almost need to create a three-dimensional image with a rotating circle moving through space in order to visualize what the tangent and the cotangent and the inverse trig functions are doing. But here it's fairly clear. The tangent line is just the line here, and it's broken up into these two pieces. Now, these two pieces on a 45, 45, 90 triangle are of equal length. I'd love to know what this whole line is called. It may just be called the tangent line, I don't know. But since we're calling this segment cotangent and this segment tangent, I'd like to know what this whole thing is called. Again, if you can find that, please let me know. Just to finish out, I'll show this again, that we did do this. And I don't know how whoever created this used or what they used, but we use sacred geometry to find ours. It's remarkable how much can be done with the sacred geometry. Interestingly, we're not doing math in this video, but since I know this right here is square root of 2 over 2, because remember our sine was square root of 2 over 2 because it's a 45, 45, 90 triangle. And I know that the distance from the point at which the unit circle hits the y-axis and the origin point, I know that is 1. I know that distance is 1. That, by the way, if I can extend out here a little bit, this distance here, let's not lose sight of this. This is 1. This is square root of 2 over 2. And this point here is the sine of 90 degrees. That's 1. So if I wanted to know what the cosine was, I could take 1 and subtract out my sine to get the cosine. So I'm not going to do the math, but the cosine here would just be equal to uh, 1 minus this distance here. I mean, it's visually obvious, but this distance here would be the sine of 45 degrees, which is square root of 2 over 2. And so you could say the cosine of 45 degrees is equal to the sine of 90 degrees minus the sine of 45 degrees. Do you see why? Because the 1 is the sine of 90 and the square root of 2 over 2 is the sine of 45 degrees. So there we know the cosine because we know these other 2 points. And that's how we can begin to build. In my education, I would have been presented with a formula like this and said, memorize that. And I honestly was never shown anything like this construction, a video like this, ever in my life. And I couldn't even find one on the internet. I found the image here. This is how I did this. I found this image, which was very helpful. And I'm sure that at some point when I took Trig in college, that this image was shown to me, but I don't ever remember anyone sitting down and walking through it laboriously, slowly, carefully, and certainly no one showed the sacred geometry. Never. But I would have been presented this complicated formula in a textbook with few pictures and never shown how to do it, but tested on it. That would be said, what is the cosine of 45 degrees? And I was just lost. So if I had an unlimited amount of time on that test, I could draw all this out and just read it off the graph or the curves, the segments and the lines. I hope this has been helpful. And if you have requests that you would like me to show a video of what to do or how to do it, please let me know. I could make another video like this for a 30, 60, 90 triangle to see if any other cool relationships exist. But that will conclude the purpose of today's video. I'll leave you with a moment of Zen. This is the drawing from Leonardo da Vinci, and you can see how he was very interested in the sacred geometry. So that will conclude the video. Thank you for watching, and I hope it was helpful to you.